Good morning, friends. Up to this, we discussed about the interference, and also we discussed in interference the constructive and destructive interference, and we obtained the condition for path difference and phase difference, and also the intensity of the light at a point at which two or more than two waves are superposed. Clear? Okay. On the basis of this interference, we are going to discuss the numerical of exercise. First is given the wavelength, a monochromatic light of wavelength 589 nanometer incident on a water surface. Find the wavelength, frequency and speed of a light for reflected wave and the reflected ray and reflected ray. And refractive index of water is given n is equal to 1.33. Now what this numerical suggests that there is the surface of the water. Now there is the perpendicular overhead point of incidence. One ray of light is incident on the water surface and angle of incidence is I. So here this incident ray reflected and also refracted. Now there is the reflected ray and reflected ray is in water medium. There is water, there is the air medium. Effect index of A is 1 and for water n is 1.33. Here this thing, there is the incident ray and that is reflected ray. That is reflected ray. This figure is only for understanding. Here we have to find out what is the wavelength, frequency and speed of reflected ray. Now the reflected ray is in the same medium, that means in air medium. That means the incident ray and reflected ray both are in same medium. Therefore the speed is in same. Wavelength is also same, only the frequency is changed. Here we are going to calculate the frequency and also the wavelength and also the speed. First, for reflected ray, that is in a medium. Therefore, wavelength of a light is same as the wavelength of incident wave. Therefore, lambda is equal to 589 nanometer. Second, frequency of a light. Okay, we know that the C is equal to F lambda. Therefore, F is equal to C by lambda. F is equal to C by lambda. C is equal to 3 into 10 is to 8 upon lambda is equal to 589 nanometer, convert into meter, so into 10 is to minus 9. Therefore, frequency is 5.092 into 10 is to 14 Hertz. Therefore, the frequency of reflected wave in a medium is this. Therefore, F is equal to 5.092 into 10 is to 14 Hertz. Now, third part, speed of a light in a medium. So that is the C. C is equal to 3 into 10 is to 8 meter per second. Now, second portion, reflected ray. Reflected ray in water medium. Because after the reflection, the reflected rays propagate in water medium. Therefore, the wavelength, first, wavelength of reflected ray That is the lambda dash is equal to lambda upon n. So in other medium, then the wavelength in A medium divided by the refractive index of a given medium. Therefore, pi 89 into 10 is to minus 9 divided by 1.33. Therefore, 442.86 into 10 is to minus 9 meter or 442.86 nanometer. That is the wavelength of reflected. Now, second part, frequency. What is the frequency of dash of reflected? Now listen, frequency does not change with the change in medium. Frequency of a ray does not change with medium. It remains constant. Therefore, f dash is equal to f. What are the frequency we obtained? This 5.092 into 10 is to 14. So 5.092 into 10 is to 14 Hertz. Now, third part, what is the speed of reflected ray in given medium? For that purpose, we know that from the refractive index, we know that the n is equal to c by v. So v is equal to c by n. C is 3.3 into 10 is to 8 upon 1.33. Therefore, 2.256 into 10 is to 8 meter per second. That is the speed of the reflected ray in water medium. Here is okay. Now the second numerical. What is the shape of a wavefront? If the light is immersed out from the point like source, the shape of a wavefront. For following cases, first, light emerges out from a point source. If the light is emerged out from the point source, what's happened? We do the diagram like this way. Light is emerged out from the point like source. So in all direction, the light is propagating with the same speed. Therefore, the waves or the wavefront emerging out from the point like source are propagating in three-dimensional, homogeneous and isotopic medium are spherical in shape. Because all the points on the surface of a sphere oscillate with the same phase. So here all the points are oscillating with the same phase. As we do the one ball sphere at a quite large distance, all the points on the surface of this sphere also oscillate with the same phase. Now, as we do the rays like this way, so what's happened? So this wavefront like this way. So that is the spherical wavefront. That is the spherical wavefront. Thus, the shape of the wave emerging out from the point-like source is the spherical wavefront. We do the clear diagram like this thing. So as shown in the figure, here the waves emerge out from the point-like source. So here you consider here is the point source. So we consider the rays emerging out from the point source like this way. So this shape of the wavefront. Now at quite large distance, so there is the spherical wavefront. And this is the light emerging out. Therefore, if now the wavefronts emerging out from a point source propagating in three-dimensional homogeneous isotropic medium are spherical in shape. Spherical in shape. Because all points on a sphere oscillating in same phase. Therefore, the wavefront emerging out from the point source is the spherical wavefront. Here is okay. So, by using the concept of the wavefront, we can judge about that which shape of the wavefront is produced by the point-like source. Now, second portion of this numerical 10.2. What is the shape of the wavefront if the light or the wavefront emerging out from a convex lens for which a point-like source is placed at principal focus of a convex lens? So, what is the figure for this question? So, here the point-like source is placed at principal focus of a convex lens. That is the convex lens. Point-like source is placed here. So the ray coming from the point-like source are incident on a convex lens, and after the reflection, this rays becomes the parallel. This rays becomes the parallel. Therefore, the plane wavefront is obtained. The plane wavefront is obtained like this way. Another wavefront is also the plane wave. these are the plane waves. So these two are plane wave front. There is the point light source and the point source. There is convex lens. Convex lens. Now listen how we act. It's shown in figure. It's shown in figure. The light emerging out from a convex lens is parallel rays because point light source is placed at principal focus of a lens, convex lens, so that wavefront is plane wavefront. Now third part, the wavefront emerging out from the distant star and observed from the surface of the earth, or the interpreted by the earth. So what's happened actually? One star is at far distance, so the light emerging out is propagated in 3-dimensional, homogeneous and isotopic medium. Therefore, actually, the spherical wavefront are generated from the star. But our Earth is at very large distance from the star. So when this spherical wavefront reaches on the surface of the Earth, at that time, small portion of this spherical wavefront is observed as a plane wavefront. Therefore, a small portion of the wavefront emerging out from the star, which observed from the Earth, is plane wavefront. Right? Now, there is the star and there is the Earth. The wavefronts emerging out are spherical wavefront. But small portion of such wavefront at large distance, that means observed from the Earth, becomes as a plane wavefront. So that is the plane wavefront we feel on the surface of the Earth. Now, thought. In point, what is the speed of light in glass medium? The effective index of a glass medium is effective index of a glass. n is equal to 1.5. We have to find out the speed of light in glass. That means the V we have to find out. That is our first portion. Now listen, from the definition of the effective index, n is equal to c by v. From equation, n is equal to c by v. Therefore, speed of light in dispersive medium or in glass, v is equal to c by n. Now, velocity of light in vacuum or the air medium, 3 into 10⁸ upon n 1.5. So it's equal to 2 into 10⁸ meter per second. That is the speed of light in glass medium. Now, second B portion. Now, speed of light is independent of color. If not, so out of violet and red color, which color has the less speed in glass prism or the slower speed in glass prism? First, we have to discuss about that. The speed of light depends on the color. Therefore, if the frequency is more, if frequency is more, the effective index is also more or the high. But the speed is less, but speed of a color is slower or the small. Color depends on the frequency of the light. And now, color of the light depends on frequency of the light. Frequency of a light. Now, frequency of the blue light is more. We know that from red to violet, right there. But frequency of blue color, that means the violet, is more than the frequency of red color. Therefore, the speed of red color is more. Therefore, speed of blue color is slower than the speed of red. Speed of red in dispersive medium. Dispersive medium or the glass medium. Thus, the speed of the light depends on, is not independent of color or the frequency. Thus, the speed of a light is not independent. Actually, there is the depends on. Color, that means the frequency of a light. Frequency of a light. So keep in mind this second portion of this numerical may be asked in NEET exam or the competitive exam. And earlier in chapter first numerical, we discussed about that the frequency in glass medium of a given light. The frequency of a frequency of a light in different medium does not change. That is the main constant. But here the speed is changed in as the medium is changed, and the color of a light depends on the frequency of a light. So here we discuss this thing. Clear this? Now, fourth numerical of exercise is given as in Young's double slit experiment, the separation between the two slits is 0.28 millimeter. That means the D is given as 0.28 millimeter. And the screen is placed at 1.4 meter distance from the slit. Therefore, capital D is given as 1.4 meter. Now, the distance between the central bad fringe and fourth bad fringe, that means the n is equal to 4 for the bad fringes, is given as 1.2 centimeter. 1.2 centimeter. Find the wavelength of the light used in this experiment. Now here Young's double slit experiment is given. So yes, we do the sketch. That is not important for our this numerical, only for understanding. Here the two slits S1 and S2. This separation is given the D. The screen is placed at capital D distance. There is the central bad fringe is n is equal to 0. Now, fourth bad fringe is n is equal to 4 at this distance. This distance is given the x4. We have to find out the wavelength of the light used in this experiment. Here, the bad fringes are given. Therefore, at this point, the constructive interference takes place. Therefore, for nth order, constructive interference at that time x and d upon capital D is equal to n lambda. There is the path difference x and d upon d is equal to n lambda. Here n is equal to 4. Therefore, x4 d upon capital D is equal to 4 lambda. Now, we require the lambda. Therefore, lambda is equal to x4 small d upon 4 capital D. Substitute the value x4 1.2 centimeter. Now D is given in millimeter, convert into centimeter. Therefore, 0.28 into 10 is to minus 1 centimeter. The similar way, D is given 1.4, convert into centimeter. So 1.4 into 10 is to 2 centimeter. Substitute this value, 0.28 into 10 is to minus 1 upon 4 into capital D, 1.4 into 10 is to 2. So as we simplify this, so we obtain 6 into 10 is to minus 5 centimeter. That is the wavelength. Now we convert into the angstrom. 1 angstrom is equal to 10 is to minus 8 meter. Therefore 10 is to 8 centimeter is equal to 1 angstrom. Therefore 6 into 10 is to minus 5 into 10 is to 8 angstrom. Therefore 6 into 10 is to 3 angstrom. It means the 6,000 angstrom. The wavelength used in Young's double slit experiment is 6,000